Welcome back to the Deep Dive. Today, we're embarking on a really fascinating journey into the human eye and the colorful world. Now, this chapter, as anyone preparing for board exams or, competitive tests like NEET and UPSC General Science knows, it's just absolutely crucial. I've been really eager to dive deep into this one and truly get a firm grasp on all its nuances.
That's a fantastic place to start our session, and honestly, your enthusiasm is spot on. This particular deep dive, well, it's an absolute cornerstone, not just for a big chunk of your Class 10 physics syllabus, but also, for building that foundational understanding. It'll really serve you well in higher-level competitive exams, too.
Right.
Think of it as a kind of natural progression from our last discussion on the refraction of light by lenses. Remember how we explored how different lens types bend light and form images?
Yes, I do.
Well, that very understanding forms the bedrock, the absolute foundation for appreciating this remarkable organ, the human eye. And beyond the exams, honestly, this chapter is truly an eye-opener, if you'll pardon the pun. It really demystifies so much of our everyday experience. Everything from the simple act of seeing the vibrant world around us to understanding why some people need spectacles, to breathtaking natural things like a rainbow, or even something as common as, why the sky appears blue.
Yeah, all those everyday things we just take for granted.
Exactly. And for your upcoming exams, whether it's your Class 10, CBSE, any state board exam, or those general science sections in SSC, CDS, CAPF, and even the basic science part of the UPSC Civil Services exam, this topic carries substantial weight, really significant. So our mission today, it's to unpack these core concepts, nail down those crucial definitions, and explore the fascinating phenomena step by step. We want to make sure every detail is crystal clear and, most importantly, equip you with the knowledge to confidently tackle any question that comes your way. #tag the deep dive. Okay, so let's kick things off by truly appreciating the marvel that is the human eye. I mean, this organ is arguably our most valuable and sensitive sense organ. Just think for a moment about how absolutely vital sight is. While our other senses, like smell or taste, they can help us identify certain things, it's practically impossible to truly experience the amazing range of colors or the tiny details of distant objects without our eyes. That fact alone really underscores its immense significance, doesn't it?
It really does. You don't often stop to think about it like that.
Yeah, right. So, to understand how it works, let's use a very helpful analogy. Picture the human eye as a really sophisticated natural camera. Just like a camera has a complex system of lenses that form an image onto a light-sensitive sensor or, film in older cameras, our eye uses a strikingly similar and incredibly efficient mechanism.
Okay, a natural camera. I like that analogy.
It helps, yeah. So let's take it piece by piece, component by component, understanding the structure and the vital function of each part. First up, when light rays enter your eye, the very first thing they hit is the cornea. This is a thin, totally transparent membrane that forms that sort of distinct, transparent bulge right on the front surface of your eyeball. Think of it like the clear, protective front window of your eye.
Got it, the front window.
Now, here's a really crucial point for your understanding, especially, for exams. The majority, and I mean most of the refraction, that's the bending of light rays as they enter the eye, happens right there at the outer surface of the cornea. It does the bulk of the initial sort of coarse focusing.
So most of the bending happens right at the start.
Exactly. The cornea does the heavy lifting initially. The eyeball itself, well, it's roughly spherical in shape, typically with a diameter of about 2.3 centimeters. This just gives it the overall structure that holds all these delicate parts. Next, right behind the cornea, we find the iris. Now, the iris is a dark, muscular diaphragm. You're probably familiar with it already. It's the colored part of your eye, brown, blue, green, hazel, that's your iris.
Right, the part that gives the eye its color.
Precisely. And its main job, it actively controls the size of the pupil. The pupil, in simple terms, is just that opening right in the very center of the iris. It looks like a dark circle. Now, for that camera analogy again, think of the iris like the diaphragm in a camera controlling the aperture, and the pupil, that's the aperture itself.
Okay, so iris controls pupil. Pupil is the hole.
You got it. It precisely regulates and controls the exact amount of light that's allowed to enter your eye. For example, if you suddenly walk into bright sunlight, your iris automatically contracts, making the pupil smaller. Why? To restrict too much light from getting in. Conversely, if you go into a dim room, the iris dilates or widens the pupil, letting more light enter so you can see better. It's this amazing automatic adjustment.
That is pretty cool.
Isn't it? Immediately behind the pupil is the crystalline lens, often just called the eye lens. Now, unlike the cornea, which has a fixed curve, this lens is made of a unique fibrous, sort of jelly-like material. And this composition gives it a truly remarkable ability, which we'll talk more about soon. It can actually change its shades. So while the cornea does that initial major refraction, the crystalline lens provides the finer adjustment of focal length. Its specific job is to make sure light from objects at different distances is focused perfectly onto the retina. And just like a converging lens in a camera, it forms an inverted, real image of the object on the retina. Remember that. Inverted and real.
Inverted. So we see things upside down initially.
The image formed on the retina is inverted, yes. But we'll get to how we perceive it correctly in a moment. First, the retina. This is a delicate, light-sensitive screen or membrane located right at the very back of the eye. This is where the image capture really happens. The retina contains a huge number, an enormous number, of specialized light-sensitive cells. Think rods and cones, though we don't need to detail them right now. When light falls on these cells, they get activated. They basically convert the light energy into electrical signals.
Light to electricity, essentially.
Essentially, yes. These complex electrical signals are then gathered up and sent from the retina along bundles of nerve fibers. These bundles together are known as the optic nerves, and they travel all the way to your brain. Finally, it's your brain that takes on the absolutely crucial role of interpreting these complex electrical signals. It processes all the information packed into them, allowing you to perceive objects not as those inverted images formed on the retina, but as they truly are right side up in full detail and with all their vibrant colors. The brain flips the image for us.
That's a crystal clear breakdown. So if I'm getting this right, the cornea is like the main fixed lens, doing most of the bending first. Then the eye lens does the fine-tuning, the precise focusing, and the retina acts almost exactly like the sensor or the film in a camera, capturing the image and turning it into signals for the brain.
Precisely. You've absolutely nailed the core concept there. That camera analogy really holds up beautifully, doesn't it? The cornea provides that coarse focusing power, handling the bulk of the light bending as rays first enter, like setting the main zoom maybe. The crystalline lens then takes over for the fine-tuning, making those subtle, really precise adjustments to the focal length. This ensures the image is perfectly sharp on the retina, whether you're looking at something miles away or reading a book right in front of you. And yes, the retina is absolutely analogous to the digital sensor or the film. It's the light-sensitive surface where that real inverted image is physically formed and then converted into those vital electrical signals ready for your brain to interpret and turn into the world you actually see. Right, now that we've got a solid handle on the eye's structure, let's delve into one of its most, well, astonishing capabilities, the power of accommodation. This is a really key concept, essential for both your board exams and competitive tests. It defines the eye lens' inherent ability to adjust its focal length. It's how your eye can effortlessly shift focus from, say, a distant cloud to the words on this page almost instantaneously. And you don't even consciously think about it. This flexibility is it's a marvel of natural engineering.
That instant refocusing always seemed like magic. So that's accommodation.
That's accommodation in action. Let's break down the mechanism behind it. As we said, the crystalline lens isn't rigid. It's made of that fibrous, jelly-like material. Its curvature, and therefore its focal length, can be actively changed. And this change is managed by a special set of muscles called the ciliary muscles. They're directly connected to the eye lens.
Ciliary muscles, okay.
Here's how this dynamic process works, step by step. When you're looking at distant objects, maybe a faraway tree or a building, your ciliary muscles are in a relaxed state, totally relaxed. When these muscles relax, they actually reduce the tension on the tiny ligaments holding the lens. This allows the eye lens to flatten out, becoming thinner and less curved, less convex. Now, when the lens becomes thinner, its focal length increases. This longer focal length is perfect for bringing those nearly parallel light rays from distant objects to a sharp focus right on your retina. Clear, distant vision achieved.
Relaxed muscles, thinner lens, longer focus. Got it.
Exactly. Now think about shifting your gaze to something nearby, like reading this text or looking at your watch. In this case, the ciliary muscles contract. This contraction increases the tension on those ligaments, causing the eye lens to become more curved. It bulges out, gets thicker, more convex. Consequently, its focal length decreases. This shorter focal length provides the extra converging power needed to bring the diverging light rays from nearby objects to a sharp focus precisely onto your retina. allowing you to see close-up details clearly. It's an automatic, continuous adjustment, happens without you doing anything consciously.
Wow. So muscles contract, lens gets thicker, shorter focus for near objects.
You've got it. But this incredible ability isn't limitless. The eye lens can't just keep getting thicker and thicker, decreasing its focal length forever. Try reading a page by holding it really close to your eyes, maybe less than 20 centimeters. You'll notice the image gets blurry, right? And you might feel some strain in your eyes.
Yeah, definitely. It gets uncomfortable.
Exactly. For comfortable, distinct vision, a young adult with normal vision typically needs to hold an object at about 25 centimeters from their eyes. This minimum distance, where objects can be seen most distinctly without any strain, is called the least distance of distinct vision, or, more commonly, the near point of the eye. And for a young adult with normal vision, that value is approximately 25 centimeters. Remember that number, it's important for numerical.
25 centimeters, a near point.
Okay. Then, on the other end of the spectrum, we have the far point of the eye. This refers to the farthest point up to which a normal eye can see objects clearly. For a healthy, normal eye, the far point is considered to be at infinity. You can see stars, which are practically an infinite distance. So putting it all together, the full range of accommodation for a normal eye allows clear vision of objects anywhere between 25 centimeters and infinity. That entire vast range is covered.
25 centimeters to infinity. That's quite a range.
It really is. Now, before we move to vision defects, it's worth just briefly mentioning a common condition that can affect the crystalline lens, especially as people get older. Sometimes the lens can become milky, cloudy, losing its transparency. This condition is called cataract. This clouding leads to partial or even complete loss of vision because light can't pass through clearly. But the good news is, in many, many cases, vision can be significantly restored, sometimes fully recovered, through a relatively common surgery. They remove the cloudy natural lens and replace it with an artificial one. It's a very successful procedure worldwide.
That explanation of accommodation is incredibly clear, especially understanding how those ciliary muscles work.
Yeah.
Could you just quickly recap the core idea, how the lens actually changes its focal length? Is it purely about the ciliary muscles making it thinner or thicker?
Excellent question, and it's good to crystallize this core mechanism. Yes, fundamentally, it is all about the ciliary muscles altering the lens curvature, which directly changes its thickness, and as a result, its focal length. Let's simplify it. When the ciliary muscles relax, they effectively pull on the lens via the ligaments, causing it to flatten out. A flatter lens, thinner, defers longer focal length, perfect for distant objects. When the ciliary muscles contract, they release tension on the ligaments. The lens, being naturally elastic, bulges, becoming more curved and thicker. A thicker lens, a shorter focal length, needed for nearby objects. So it's this beautiful, dynamic interplay. Relaxed muscles mean a thin lens, long focus. Contracted muscles mean a thick lens, short focus. An elegant system ensuring clear vision across distances. Hashtag 3, defects of vision and their correction. Okay, now despite the eye's truly phenomenal power of accommodation, sometimes this ability can gradually diminish, or perhaps it's impaired right from birth. This leads to blurred vision. When this happens, a person might struggle to see objects distinctly and comfortably. These are what we call refractive defects of the eye. The good news for anyone affected is that these defects are actually quite common, and fortunately, they can often be effectively corrected using suitable spherical lenses, usually in spectacles or contact lenses. Now, this section is really, really important for your exam, so let's pay close attention.
Right, this is the part about glasses.
Exactly. There are 3 main common refractive defects of vision that you absolutely need to understand thoroughly for your board and competitive exams. First, myopia, which you probably know as near-sightedness. Second, hypermetropia, often called far-sightedness. And third, presbyopia, which is generally related to aging. Let's discuss each one comprehensively. We'll cover the symptoms, the causes, and crucially, how they are corrected. Okay, first up, A. Myopia, nearsightedness. A person suffering from myopia, well, they can see nearby objects perfectly clearly, no problem reading a book, but they experience significant difficulty seeing distant objects distinctly. For someone with myopia, their far point, remember, the furthest distance they can see clearly is much nearer than infinity. In some cases, it might be just a few meters away, or even less. Imagine trying to read a road sign across the street, it just looks like a blur, but the phone in your hand, perfectly legible. That's classic myopia.
Can't see near, can't see far.
Precisely. Now, what's happening inside the eye? For a myopic eye, the image of a distant object, instead of forming exactly on the retina, is formed in front of the retina. The light focuses too soon. This premature focusing causes that blurry, distant vision. There are 2 main reasons, or causes, for this defect. Both basically mean the eye's converging power is too strong. 1. excessive curvature of the eye lens. This means the crystalline lenses become too curved, too convex, making it overly powerful at bending light. 2. Elongation of the eyeball. The eyeball itself might have grown slightly longer than its normal spherical shape. In this case, even if the lens is normal, the retina is just positioned too far back, so the image forms before reaching it.
So either the lens is too strong or the eye is too long.
That's a great way to summarize it. Now, how do we fix it? Myopia is effectively corrected using a concave lens of a suitable power. Remember, a concave lens is a diverging lens. It spreads light rays out slightly. So when light from distant objects, which is nearly parallel, first passes through this concave lens, it diverges slightly before entering the eye. This slight pre-divergence perfectly counteracts the myopic eye's excessive converging power. It ensures that when the light then passes through the eye's own lens system, the focal point gets pushed back and converges sharply onto the retina. So you can visualize the concave lens as sort of undoing the eye's tendency to focus light too early.
Okay, concave lens spreads the light out first. Makes sense.
Good. Next, B. Hypermetropia, far-sightedness. Now, hypermetropia presents almost the opposite challenge. A person with hypermetropia can see distant objects clearly, no problem, but they find it difficult to see nearby objects distinctly and comfortably. For them, their near point, the closest distance they can see clearly, is farther away than the normal 25 centimeters. You might see someone with hypermetropia holding a book or newspaper much further away, maybe at arm's length, just to read it comfortably.
Can see far, can't see near. The opposite of myopia.
Exactly the opposite. This happens because light rays coming from a nearby object are focused behind the retina. The light doesn't converge enough by the time it reaches the retina. The typical causes for hypermetropia are related to the eye's converging power being too weak. 1. The focal length of the eye lens is too long. This means the eye lens isn't bending light strongly enough. Its power is too low. 2. The eyeball has become too small or too short. The eyeball might be shorter than normal. Here, the retina is positioned too close to the lens, causing the image to form theoretically beyond it.
So, lens too weak or eye too short.
Perfect summary again. To correct this, we use a convex lens of appropriate power. A convex lens is a converging lens. It provides the necessary additional converging power to the eye's natural lens system. This extra boost of convergence ensures that the light rays from nearby objects, which would normally focus behind the retina, are brought forward to focus precisely on the retina. So you can think of the convex lens as giving an extra focusing boost to compensate for the eye's weak natural convergence.
Convex lens adds focusing power. Got it.
Great. Finally, C, presbyopia. This third defect, presbyopia, typically occurs as a natural part of aging. As people get older, the eye's power of accommodation gradually decreases. It becomes less flexible. For most people, this means their near point slowly recedes. It becomes harder and harder to see nearby objects comfortably and distinctly without corrective glasses. It's why many older adults need reading glasses.
So this is the age-related one.
Yes, primarily age-related. The main causes are 1. Gradual weakening of the ciliary muscles. Over time, these muscles just lose some of their strength and elasticity. It gets harder for them to contract and relax effectively to change the lens shape. 2. Diminishing flexibility of the eye lens itself. The lens itself tends to harden and become less elastic with age, losing its ability to easily change shape. Now, sometimes, especially in older age, a person might actually suffer from both myopia, difficulty seeing far, and hypermetropia, difficulty seeing near, often due to presbyopia setting in. In such cases, they commonly require bifocal lenses. A typical bifocal lens has 2 distinct parts. The upper part is usually a concave lens for correcting distant vision, while the lower part is a convex lens designed for correcting near vision, like reading. Of course, today there are modern alternatives too, like progressive lenses, which have a gradual change in power, special contact lenses, or even surgical options, offering more choices beyond traditional bifocals.
Sir, I often find it, easy to confuse which lens corrects which defect. Myopia versus hypermetropia gets jumbled in my head sometimes. Is there a simple trick or like a mnemonic you can share? Something to help remember quickly, especially under exam pressure.
That's a brilliant question, and trust me, you are definitely not alone. This is a very common point of confusion for students, especially in competitive exams where you need quick, accurate recall. Okay, here's a mnemonic that many students find really helpful. It creates a quick association. Think of it this way. For myopia, near-sightedness, the image forms too soon in front of the retina. You need to push it back by diverging the light. What lens diverges? A concave lens. And concave lenses always have negative power. So the trick is, myopia needs my minus power. Think myopia minuses.
Myopias. Okay, I like that.
Now, for hypermetropia, far-sightedness. The image forms too late behind the retina. You need to converge the light more to pull it forward. What lens converges? A convex lens. And convex lenses always have positive power. Think plus power. So the trick here is hyper needs plus power. Or think higher plus power needed.
Hyper needs plus. Okay, myopia minus hyper plus. That actually helps a lot.
Good. If you can just lock that in. Myopia, hyper plus. You'll quickly recall the correct lens type and the sign of the power. Practice linking the problem, image in front behind, with the solution, diverge, converge. And the lens, concave and convex, it'll stick. #tag 4 numerical problems on lens correction. All right, fantastic. Now that we've firmly grasped the concepts behind eye defects and corrections, let's put that knowledge into practice. Let's solve some numerical problems. These types of questions are incredibly common, and they carry significant marks in both your board exams and various competitive exams. Think JEE, main physics, NEAT, and definitely the general science sections of UPSC, SSC, state PSCs. Mastering these calculations is absolutely essential.
Yeah, the numericals always seem tricky.
They can seem that way, but if we're methodical, they become quite manageable. Let's walk through them step by step, exactly how you should approach them in an exam. Problem 1, based on Q5. A person needs a lens of power minus D5.5 dioptries for correcting his distant vision. For correcting his near vision, he needs a lens of power plus 1.5 diopter. What is the focal length of the lens required for correcting eye distant vision and near vision? Okay, first step, always. Clearly state the given information and recall the formula we are given. Power for distant vision, let's call it P distant, and N is 5.5 dioptries D. Power for near vision, P near plus 1.5 dioptries D. The key formula linking power P and focal length F is power P equals 1 focal length F. And crucially, remember, focal length must be in meters for this formula. Conversely, focal length F equals 1 power P.
So P equals 1 with F in meters.
Exactly. Let's solve part 1, correcting distant vision. We have P distant, N is 5.5 D. Using the formula, if distant equals 1, P distant. So F distant equals 1 and V is 5.5. Now let's calculate that. 1 divided by N is 5.5. It comes out to approximately maybe just 0.118 or 8 meters. To make it perhaps more intuitive, let's convert that to centimeters. We multiply by 100. F distant equals 0.18 on 8. 100 equals in ages, and it could be 18.18 centimeters. Notice the negative sign in the focal length. What does that tell us about the lens type?
A native focal length means concave lens, which corrects myopia, distant vision. It matches.
Perfect. See how it connects. Now part 2, correcting near vision. We have key nearest plus 1.5 D. Using the formula, F near is 1 P near, so phi near is 1 plus 1.5. Calculating this, 1 divided by 1.5 gives approximately plus 0.666 centimeters. Okay. Converting to centimeters again, multiply by 100. Phi near plus 0.666, 100 plus 66.67 centimeters, and the positive sign here indicates
Positive focal length, convex lens. For hypermetropia, near vision, it works out again.
Exactly right. So the answer is, for distant vision, a concave lens with F equals 18.08 centimeters is needed. For near vision, a convex lens with F plus 66.67 centimeters is needed. Great. Let's move to problem 2, based on Q6. The far point of a myopic person is 80 centimeters in front of the eye. What is the nature and power of the lens required to correct the problem? Okay, this is a very standard and important type of problem. Analyze the situation carefully. A myopic person's far point is 80 centimeters. This means without glasses, they can only see clearly up to 80 centimeters. A normal eye sees clearly up to infinity. So what should the collective lens do? It should take an object that is at infinity, which the person wants to see clearly, and form its virtual image at the person's far point, 80 centimeters. Why? Because the myopic eye can focus clearly at 80 centimeters, so the lens creates an image there for the eye to see.
Okay. The lens brings the image of the distant object to where the eye can see it.
Precisely. Now let's list our knowns using the sign convention. Very important. Object distance. The object we want to see is at infinity, so U into infinity, conventionally negative. Image distance, V. The lens needs to form a virtual image at the far point, which is 80 centimeters in front of the eye lens. Images in front are virtual and taken as negative. So V in eugenicity 80 centimeters. Be careful with units for calculation later. Let's convert V to meters. V equals 0.8 meters.
U need is infinity. V equals 0.8 meters.
Got it. Now we use the lens formula. 1F equals 1V, 1U. Substitute the values. 1F equals 1, 0.8. 1 infinity. Now what is 1 divided by infinity?
0.
Exactly. It's effectively 0. So the equation simplifies beautifully. 1F equals negative is n equal 0.8, 0.1F equals negative 8.8. 1F equals 1.25. Finally, the question asks for the nature and power. P equals 1, where F must be in meters. P equals 1 and equal 0.8 meters. P equals 1 is 0.25 dioptries. Since the power is negative, what's the nature of the lens?
Negative power. Concave lens.
Perfect. Concave lens, power minus 1.25 D. That's the complete answer. Ready for the last one? Problem 3. based on Q7. Make a diagram to show how hypermetropia is corrected. The near point of a hypermetropic eye is 1 meter. What is the power of the lens required to correct this defect? Assume that the near point of the normal eye is 25 centimeters. Okay, the diagram part. We can't draw it here, but let's visualize it clearly. This is crucial for exams. For hypermetropia, remember, light from a nearby object, like at the normal near point, 25 centimeters, focuses behind the retina. To correct it, we need a converging lens, a convex lens placed in front. This convex lens starts converging the light rays before they enter the eye. This pre-convergence ensures that when the light goes through the eye's own lens, it finally focuses precisely on the retina. So imagine rays from an object at 25 centimeters passing through the convex lens, entering the eye, and hitting the retina sharply. That's the visual.
Okay, visualizing the convex lens adding convergence.
Good. Now for the calculation, this is key. The normal near point is 25 centimeters. This is the distance at which the person wants to see clearly, like reading a book. So for our corrective lens, the object distance on GIP's 25 centimeters, object in front negative. The hypermetropic eye's actual near point is 1 meter, which is 100 centimeters. Without glasses, they can only focus clearly on things 100 centimeters away or farther. So the corrective lens must take the object at 25 centimeters and form a virtual image of it at the person's actual near point, 100 centimeters. This virtual image acts as the object for the hypermetropic eye to focus on. Since the image is virtual and formed in front, the image distance V equals 100 centimeters.
Right, so U in X is 285 centimeters, V Gillig is 900 centimeters.
Yeah.
That step is tricky, understanding where the image needs to form.
It is tricky, but logical if you think about what the lens needs to do for the eye. Now apply the lens formula. 1F equals 1V1. Substitute carefully, watching the signs. 1F was 100 centimeters, 125 centimeters. 1F will explain about 100 plus 125. Okay, common denominator.
100, so it's negative 1100 plus 4100.
Perfect. 1F equals 1F1 plus 4, 100. 1F equals 3, 100. So at the focal length, F equals 1003 centimeters. Now for power, we need F in meters. F equals 1,300 meters equals 13 meters, which is about 0.333 meters.
Right, now calculate power P equals 1. F, P equals 113, P equals 3 diopters. And since the power is positive.
Positive power, convex lens, which is correct for hypermetropia. It all fits.
Exactly. Convex lens, power plus 3D.
Wow. This step-by-step approach for the numericals, especially breaking down the logic first, is incredibly helpful. It's easy to just jump into the formula and get lost. What would you say is the single biggest mistake students tend to make with these power and focal length calculations? The one thing to be really careful about in exams?
That's a crucial question, and it points directly to where most marks are unfortunately lost. The single biggest mistake, by far, usually involves 2 related things: incorrect use of sign conventions and errors in unit conversions.
The signs and the units. Absolutely. First, sign conventions. You must be consistent. Apply the Cartesian sign convention rigorously. Remember, object distance U for real objects, usually placed left, is negative. Image distance V for virtual images, formed on the same side as object, like in these corrections, is negative. Real images, formed opposite side, are positive. And crucially, focal length F for concave lenses is negative, for convex lenses is positive. Mixing these up, even if your number is right, gives the wrong lens type and costs marks. Getting a positive F for myopia correction, that's conceptually wrong.
So double check every sign.
Every single one. Second, unit conversions. Power in dioptries is defined as 1 over focal length in meters. Many students calculate F in centimeters, which is often easier initially, and then just plug that centimeter value into P1F. That's wrong by a factor of 100. Always, always convert your final focal length to meters before calculating the power. If F 25 centimeters, use P as 1.25 meters, not 120.
Okay, meters for power, got it. Signs in meters.
Pay meticulous attention to those 2 signs of U, V, F, and converting F to meters for P, and you'll dramatically cut down errors in these very common exam questions. Okay, before we switch gears completely and look at optical phenomena outside the eye, let's just take a brief moment to touch upon something really important. A social and ethical aspect connected to vision. Eye donation. This isn't just something that might pop up in general awareness sections of exams like UPSC or SSC. It also prompts really important discussions about social responsibility, about compassion, and the incredible impact one person can have.
Eye donation, right. That's a really important topic.
It truly is. The impact is just profound. Life-changing. Our eyes, specifically the cornea, can actually remain viable, usable, even after we pass away. By choosing to donate one's eyes, an individual can literally light up the life of someone who is blind. Think about this. Corneal blindness, that's blindness caused by damage or disease affecting the cornea. It affects millions of people globally. And tragically, a significant number are children, often under 12. For many of these people, their sight can be completely restored through a corneal transplant using donated eyes. It is honestly a tremendous and invaluable gift.
Millions.
And it's
Especially children. That's staggering.
It is. So here are some key points about eye donation. Good for general knowledge, and potentially for exams too. Eligibility. It's much broader than people often think. Donors can be of any age or sex. And many common health issues don't disqualify you. People who wear glasses, had cataract surgery, have diabetes, hypertension, asthma. If they don't have specific communicable diseases, they can usually still donate. Procedure post-death. This is vital. For transplantation, eyes need to be removed within a critical window, 4 to 6 hours after death. So it's crucial to inform the nearest eye bank or hospital immediately if the person wished to donate. The eye bank team handles the removal, often at home or the hospital. It's a simple procedure, takes maybe 10-15 minutes. And importantly, it causes no facial disfigurement. That's a common worry, but it's unfounded. Ineligibility. Safety first, always. People who died from or had certain infectious diseases like AIDS, hepatitis B or C, rabies, acute leukemia, tetanus, cholera, meningitis, encephalitis, unfortunately, they cannot donate due to the risk of transmission. Impact. This is amazing. A single pair of donated eyes can potentially give sight to up to 4 corneal blind people, because sometimes different parts or layers of the cornea can be used for different recipients.
Wow. 1 pair for up to 4 people.
Incredible, isn't it? Eye banks are crucial here. They collect, evaluate medically, preserve, and distribute the donated eyes ethically and efficiently. Even eyes not suitable for transplant can be used for vital research and education. And throughout the whole process, the identities of both the donor and the recipient are kept strictly confidential.
That's a truly powerful and insightful look into eye donation. It's quite humbling, actually. Astonishing to think one decision can have such a massive lasting impact, literally illuminating someone's world. It really makes you appreciate our own sight even more.
Indeed. It's a testament to human compassion, isn't it? How we can offer the gift of light even beyond our own lifetime. A powerful thing to think about and a mark of responsible citizenship. #6. Refraction of light through a glass prism. Okay, so we've explored the eye itself. Now let's shift our focus to how light behaves when it encounters a different kind of optical tool. The glass prism. You'll remember from our earlier discussions, we talked quite a bit about light refracting through a rectangular glass slab. The key takeaway there was that for parallel surfaces, like a slab, the emergent ray comes out parallel to the incident ray, just shifted sideways slightly, remember?
Yes, parallel but laterally displaced.
Exactly. But a prism, with its unique shape, its inclined surfaces, behaves quite differently. And this leads to some really interesting and visually striking effects. So what exactly is a triangular glass prism? Well, the name gives it away. It's usually a transparent solid made of glass with 2 triangular bases and 3 rectangular lateral surfaces. These rectangular surfaces aren't parallel, they're inclined at an angle to each other. And the angle between 2 of these faces, the ones light usually enters and leaves through, is called the angle of the prism. This angle is key to how it bends light.
So the non-parallel sides are the important bit.
That's the crucial difference from a slab. Now, to really visualize the path of light through a prism, let's imagine doing a classic experiment, like Activity 10.1 in your textbook. Visualizing this is key for drawing diagrams in exams. Imagine placing a prism on white paper, tracing its outline. Let's call one refracting face AB, the other AC. Now, draw a line, PE, hitting face AB at an angle. This PE is your incident ray. You'd fix 2 pins, P and Q, along this line. Now, the crucial part, look through the other face, AC. Find the images of pins P and Q. Then, fix 2 more pins, R and S, on the paper so that RS and the images of P and Q all line up perfectly straight when viewed through face AC.
Okay, lining up the pins through the prism.
Exactly. Then remove everything. Connect the dots. PE is the incident ray. The line segment, EF, inside the prism is the refracted ray. And the line FS, where light comes out of face AC, is the emergent ray.
Now, let's look at the bending at each surface. At the first surface, AB, air to glass, light enters a denser medium, so it bends towards the normal. At the second surface, AC, glass to air, light exits into a rarer medium, so it bends away from the normal. Now here's the key difference from the slab. Because the 2 refracting surfaces, AB and AC, are inclined, the emergent ray, FS, is not parallel to the incident ray, PE. Instead, the emergent ray is bent at a specific angle relative to the original direction of the incident ray. This significant angle is super important in optics. It's called the angle of deviation, AD. It's specifically the angle between the incident ray's original path, if it had gone straight, and the final path of the emergent ray. This predictable bending and deviation make prisms incredibly useful in optical instruments.
So the prism doesn't just shift the light, it actually bends it quite dramatically, leading to that angle of deviation. Is that fundamental property why prisms are used in so many things, like binoculars or maybe even scientific stuff?
You've grasped it perfectly. That's exactly why prisms are so valuable. Unlike the parallel slab, where light goes in and comes out parallel, the prism's inclined surfaces cause a much more substantial, predictable change in direction. This precise control over bending light, producing a specific angle of deviation, is indeed why prisms are fundamental in countless optical instruments. They can deviate beams, invert images, or as we'll see next, split white light into colors. And for those aiming for JE or NEAT, you'll later study how prisms can even cause total internal reflection, making them vital in things like periscopes and even fiber optics. Highly versatile. #7. Dispersion of white light by a glass prism. And that leads us nicely into what I think is one of those beautiful optical phenomena, the process that lets us understand how plain old white light can unfold into the stunning colors of a rainbow. This is dispersion.
Ah, rainbows. Okay, I'm interested.
Right. So let's imagine another simple but profound experiment, like activity 10.2. Take a piece of cardboard, make a tiny hole or a narrow slit in it. Let a narrow beam of white light, maybe sunlight, fall onto this slit. You get a nice thin beam. Now place a glass prism in the path of this beam so the light hits one face, then put a white screen on the other side where the light comes out. What do you think you'll see on the screen?
Based on the topic, probably not just a white spot, maybe colors.
Exactly. You won't see a white spot. Instead, you'll see a magnificent, distinct band of colors. This band of colored components that forms when light is split is called its spectrum. And importantly, the sequence of colors is always the same, from bottom to top. Usually, depending on orientation, you'll see violet, indigo, blue, green, yellow, orange, and red. We famously remember this using the acronym VIBGYOR.
VIBGYOR. Got it. That's the spectrum.
Precisely. And this whole phenomenon, the splitting of white light into its component colors, when it passes through a transparent medium, like a prism, that is dispersion.
Okay, but why does it split? Why does the prism do that?
Very good. Excellent question. The fundamental reason is that different colors of light actually travel at slightly different speeds when they pass through a medium like glass. This tiny difference in speed causes each color to bend, or refract, through a slightly different angle as it goes through the prism. Specifically, and this is crucial fixture, violet light bends the most. It deviates the most from its original path, while red light bends the least. Because each color in white light bends by a unique amount, they emerge from the prism along slightly different paths. They spread out, creating the spectrum we see.
Different colors, different speeds, different bending angles, violet most, red least. Okay.
You got it. Now, the great scientist Isaac Newton was the first to systematically get this spectrum using a prism. But what he did next was even more brilliant. He tried splitting the colors further with another prism, but couldn't get new colors. Then he did something clever. He placed a second identical prism, but inverted, upside down, right after the first one. When all the separated colors from the first prism passed through this second inverted prism, what did he see emerge? A single beam of white light again.
Wow, so he split it and then put it back together.
Exactly. This conclusive experiment proved, beyond doubt, that sunlight, which looks white, is actually made up of these 7 distinct colors. Dispersion is reversible.
That's a landmark experiment.
Absolutely. And this understanding of dispersion leads us directly to explaining nature's most spectacular display, the rainbow. A rainbow is basically a natural spectrum we see in the sky, usually after rain, and always in the direction opposite to the sun. How does it form? Millions of tiny water droplets left hanging in the air after rain act like miniature prisms. Each tiny raindrop does 3 things to the sunlight hitting it. First, as light enters, it refracts and disperses, splitting into colors. Second, the separated colors hit the back inner surface of the raindrop and undergo internal reflection. They bounce off the back. Third, as the light comes back out of the front of the raindrop, it refracts again. Because of this specific combination dispersion, internal reflection, and then more refraction, different colors reach your eye from different droplets at slightly different angles. This creates that beautiful arc of colors we see. You can sometimes see a similar effect looking at a waterfall or a garden sprinkler on a sunny day if the sun is behind you. Nature's optics.
Dispersion, internal reflection, refraction, inside tiny raindrops. Amazing. So the order of bending, violet most, red least, and Newton's experiment, those are key exam points, right? And does that internal reflection bit connect to other physics concepts, maybe for J or NEAT?
Absolutely, you hit the nail on the head. The order of bending violet most, red least, is fundamental to the dispersion, and a very common NCQ point in Nietzsche, Newton's recombination experiment. Crucial for conceptual clarity, and often asked directly in boards in UPSC general science. And yes, that internal reflection in rainbows is a fantastic link to higher-level physics, especially for GNEAT. While we see its basic role here, the full concept is total internal reflection, TIR. You'll study TIR in much more detail in Class 11-12 physics. It explains how optical fibers work, carrying internet data, why mirages appear in deserts, the sparkle of diamonds, all sorts of things. So understanding its role in rainbows now gives you a valuable head start. It shows how physics concepts connect from everyday phenomena to advanced tech. Okay, we've seen light bend through glass lenses and prisms. Now let's look at how it bends through something we're always in the air itself, the Earth's atmosphere. This is called atmospheric refraction.
Light bending through air. How does that happen?
Well, think about a simple example you've probably seen. Ever looked at objects through the hot air rising above a fire, or a hot road surface on a sunny day, or even a radiator? Things seem to shimmer or waver, right?
Yeah, like a heat haze. It looks wobbly.
Exactly. That's atmospheric refraction on a small scale. The air right above the heat source is hotter, making it less dense than the cooler air around it. Hotter, less dense air has a slightly lower refractive index. And because this hot air is turbulent, always moving, the light rays passing through it bend irregularly. This makes the apparent position of objects seen through it fluctuate, causing that shimmering, wavering effect.
Okay, so changing air density bends light.
Precisely. Now let's scale this up to understand some cosmic phenomena.
Yeah.
Twinkling of stars. This is a classic. Why do stars twinkle? It's entirely due to atmospheric refraction of starlight. Starlight travels vast distances through space, mostly vacuum. When it finally hits Earth's atmosphere, it enters a medium that isn't uniform. Our atmosphere gets denser as you go lower down. So as starlight passes through these layers of changing density, it continuously refracts, bending towards the normal, since it's going from rarer to denser. This bending actually makes a star appear slightly higher in the sky than it really is, especially near the horizon. But here's the key for twinkling. Our atmosphere is turbulent. Air currents, temperature changes. It's always shifting slightly. This means the path of the light rays from the star constantly varies just a tiny bit. This causes two things. The star's apparent position seems to wobble slightly, and more importantly, the amount of light entering our eye flickers. Brighter, fainter, very rapidly. That's the twinkling effect.
So it's the unstable atmosphere making the light path wobble and flicker.
Exactly. It's not the star itself changing brightness. Why planets don't twinkle? Another classic question, especially for competitive exams. Planets are much, much closer to Earth than stars. Because they're closer, we see them not as single points of light, like distant stars, but as extended sources. Think of them as tiny disks, not pinpricks. You can imagine a planet as being made up of a huge collection of individual point sources of light. While light from each individual tiny point on the planet might flicker due to the atmosphere, the fluctuations from all these points reaching your eye tend to average out. Some points get brighter, some get fainter simultaneously, and the overall effect cancels out. The total amount of light stays pretty constant. This nullifies the twinkling effect.
So stars are points, planets are disks, collections of points, and the averaging cancels the twinkle for planets. Clever.
Precisely. It's about apparent size due to distance, advanced sunrise, and delayed sunset. One more fascinating effect. Because of atmospheric refraction, we actually see the sun for about 2 minutes before it physically crosses the horizon at sunrise. And we continue to see it for about 2 minutes after it has physically dipped below the horizon at sunset.
Wait, we see the sun when it's not actually there?
Technically, yes.
Huh.
Actual sunrise-sunset is when the sun center crosses the horizon line. But because the atmosphere bends light rays, especially when light comes in at a shallow angle near the horizon, sunlight bends around the curve of the Earth and reaches our eyes even when the sun itself is still slightly below the horizon. This bending makes the sun appear higher than it is, so we see it rise a bit early and set a bit late, as about 4 minutes of apparent daylight in total. Oh, and that squashed or flattened look the sun sometimes has right at sunrise or sunset. That's also due to atmospheric refraction, bending the light from the bottom edge more than the top edge.
That's incredible. 4 extra minutes of daylight just from air bending light. So that heat haze on roads is the same basic principle, right? And is this why astronomers build telescopes way up high on mountains or in space to get above most of this distorting atmosphere.
Excellent connection. Yes, the shimmering heat haze is exactly the same principle, localized atmospheric refraction due to temperature and density differences. And you're absolutely right about observatories. Astronomers go to great lengths to build them at high altitudes, on remote mountains, precisely to minimize atmospheric disturbance. Up high, the air is thinner, less dense, and generally more stable. This means less refraction, less turbulence, which causes blurring, astronomers call it seeing, and less scattering, which we'll discuss next. It allows them to get much clearer, sharper images of faint and distant objects. And space telescopes like Hubble or Webb avoid the atmosphere altogether, giving the clearest views possible. Okay, our final section on optical phenomena deals with something called scattering of light. This is how light interacts with tiny particles in the atmosphere, and it's the key to explaining some of the most common and beautiful colors we see around us. Think the blue sky, the deep blue sea, those fiery red sunsets.
Scattering. Okay, how is that different from refraction?
Good question. Refraction is bending as light passes through a medium. Scattering is when light hits tiny particles and gets bounced off or redirected in many different directions. You might remember the Tyndall effect from class 9.
Vaguely. Something about light beams being visible.
Exactly. It's the scattering of light by colloidal particles. Remember how a light beam is invisible through clear water but becomes visible through milky water? The milk particles scatter the light, making the beam's path visible? Well, Earth's atmosphere is full of tiny particles, not just air molecules, N2, O2, but also microscopic smoke, dust, water droplets, aerosols. It's like a giant, very dilute colloid. When sunlight hits these particles, the light gets scattered in all directions. This is why you can sometimes see sunbeams slanting through a dusty room or through mist in a forest. The particles are scattering the light, making the path visible.
Ah, okay, so particles bouncing light around.
Pretty much. Now, here's the crucial part for explaining color. The color of the scattered light depends heavily on the size of the scattering particles relative to the wavelength of the light. Very fine particles, like air molecules themselves, are much smaller than the wavelength of visible light. These tiny particles are much better at scattering shorter wavelengths, meaning blue and violet light. Larger particles tend to scatter longer wavelengths, like red and orange, more effectively, or scatter all colors more equally. If the particles are quite large, like the water droplets in clouds, they scatter all wavelengths roughly equally. When all colors are scattered together, what color do we perceive? White. Exactly. That's why clouds usually look white or gray. The droplets are large enough to scatter all colors. Now let's apply this size-dependent scattering. Why is the color of the clear sky blue? This is fundamental. The molecules of air, nitrogen, oxygen, and other very fine particles in the upper atmosphere are tiny, much smaller than light wavelengths. As we just said, these tiny particles are super effective at scattering short wavelength light blue and violet. They scatter blue light far more strongly than red light. Red has a longer wavelength, about 1.8 times longer. So as sunlight streams through the atmosphere, the blue-violet components get scattered vigorously in all directions by these air molecules. This scattered blue light comes at us from all over the sky, entering our eyes. And that's why the clear sky appears blue.
So the air itself preferentially scatters the blue light everywhere.
Precisely. Now why not violet? Violet is scattered even more strongly than blue. But our eyes happen to be slightly more sensitive to blue, and the sun emits slightly less violet. Plus, some violet gets absorbed high up. The net result we perceive is blue. And this also explains why the sky looks black from space or very high altitudes, right?
Because there's no atmosphere, no particles up there to scatter the light?
Exactly. No scattering, no blue sky. Just black space with the sun, moon, and stars. Red color of danger signals. Final application. Why are stop signs, warning lights, car tail lights always red? It's because red light, having the longest wavelength in the visible spectrum, is scattered the least by particles in the atmosphere, like fog, mist, smoke, or dust. Since it's scattered less, it can travel the longest distance through the air without losing much intensity or having its path significantly diverted. This makes red light clearly visible from further away, even in poor visibility conditions. That's why it's chosen for signals where visibility is critical for safety.
Because red cuts through fog and dust the best. That makes so much sense now. So is this also the reason for red sunsets and sunrises? Because the blue light got scattered away on its long journey, leaving mostly red?
Precisely. You've absolutely nailed the connection. At sunrise and sunset, sunlight has to travel through a much thicker layer of the atmosphere to reach your eyes because the sun is low on the horizon. Along this very long path, most of the shorter wavelengths, the blues and greens, get scattered away effectively by the atmospheric particles. They go off in other directions, What's left? Primarily the longer wavelengths, the oranges and reds, which are scattered the least. These are the colors that make it all the way through that long atmospheric path to reach our eyes. This differential scattering gives us those spectacular fiery red and orange colors we see painting the sky at dawn and dusk. A beautiful daily demonstration of light scattering. #outro. All right, well, that brings us to the end of our really comprehensive deep dive into the human eye and the colorful world. We've certainly covered a lot of ground today, haven't we?
We really have. My head's full, but in a good way.
Excellent. I hope you feel much more confident about this absolutely crucial chapter now. We started with the eye itself, its intricate structure, appreciating each part's role. Then we unpack that amazing power of accommodation, how our eyes adjust focus so effortlessly. Then we systematically tackled those common vision defects. Myopia, hypermetropia, presbyopia, we looked at their causes and, importantly, their lens corrections, and definitely applied that to those essential numerical problems. Remember, those are key for exams.
Definitely won't forget the numericals now. Myopia minus hyper plus.
Perfect. Then we ventured into how light interacts with a glass prism, leading to that spectacular phenomenon of dispersion splitting white light into VIBGYR, and how that explains rainbows, thanks to Newton's brilliant insights. And finally, we demystified all those fascinating atmospheric effects, the twinkling stars and why planets don't, advanced sunrise and delayed sunset, and of course the reason for our blue sky, all down to atmospheric refraction and the scattering of light. Now, to really master this chapter for your exams, whether it's boards, NEET, UPSC, General Science, SSC, whatever you're aiming for here are a few critical tips to make sure you excel. First, visualize everything. Since we couldn't use physical diagrams today, make it a priority to practice drawing them yourself. Or diagrams for eye defects, myopia, hypermetropia correction, and light through a prism. Sketching them out repeatedly really cements the understanding. It makes the abstract concrete.
Practice the diagrams.
Yeah.
Okay.
Second, revise all key definitions and NCERT keywords thoroughly. Terms like power of accommodation, least distance of distinct vision, far point, dispersion, angle of deviation, spectrum, Tyndall effect. These are frequently asked directly, know them precisely. Easy marks often lie here.
Definitions and keywords. Got it.
Third, especially for competitive exams, solve numerical problems regularly. Aim for maybe 5 problems daily just on lens power and focal length for eye defects from this chapter. Consistent practice is the only way to get fast, accurate, and confident with the formulas, the sign conventions, and those unit conversions. Practice truly makes perfect here.
5 numericals daily. Okay, that's a concrete goal.
And finally, connect these concepts. Don't study things in isolation. See how atmospheric refraction and scattering link to everyday observations. Understand how the eye's structure enables its function. This interconnected thinking helps massively with application-based questions in competitive exams. Plus, it builds a much stronger foundation for your Class 11 physics, especially when you dive deeper into optics. So, keep practicing diligently, stay curious, keep asking why. You'll undoubtedly shine in your exams.
Thank you so much, sir. That was genuinely an incredibly insightful and thorough deep dive. I honestly feel much, much more confident about the human eye and the colorful world now. All the concepts feel crystal clear, and I definitely have a solid path for practice and what to focus on. This was a truly amazing learning session. Thank you.